Shall we begin with a word of prayer? Heavenly Father, we thank you for this day. I thank you for the student, and help us to use this time wisely, Lord. In your name we pray. Amen. Okay, so as I was just telling you, this is helpful advice for, in fact, I think it's the answer, oops, for, part of the answer for problem 129, part A. This is a basis. Of course, you should work that out. If you don't understand this, don't just write this down. So we were just discussing there's two ways you could find the projection onto the perp of A. One way is to use the basis above and just project out the pieces, right? The other way is to use the fact that since these subspaces are complementary, we had some relations between the orthogonal and the projectors, the orthogonal projector versus the parallel projector, as you might call it. So the parallel projector of W perp, which is the piece of A, which is in the W perp direction, is the same as the orthogonal projector of A, where this gives you the piece of A which is perpendicular to W. All right, so if it's perpendicular to W, that means it's parallel to W perp. That's what's in this. All right, there's this duality between perpendicular and parallel in the dual, in these two different perpendicular spaces. Now, so the way to calculate this would just be A minus the parallel piece to W, the projection onto W of A. And that's pretty easy to calculate because W is one-dimensional, and the basis, orthonormal basis, rescaling by 1 over root 2 is just this. So you can either calculate the part B as this calculation here, or you could try this calculation here. They should give us the same answer. The answer has zeros on the diagonal, and it's non-zero off the diagonal. Yeah.
So, because of the formula you wrote down, we can just use the A, so get rid of the A minus, and then that's just the projection of A?
Yeah, so like specifically this would be, I would do something like A, B, C, D, minus the inner product of A, B, C, D with, well, to be lazier, pull out a half, because this root 2 and that root 2 can pull out to be a half out here. So
And the inner product is just the dot product, right?
right, so the inner, this is just what? This is just actually A times 0 plus B times, so it's B, A times 0 plus B times 1 minus C times, C times minus 1 plus D times 0. So this inner product is just B minus C for this problem. And, yeah.
And the dot product of two matrices is almost kind of just like multiplying them.
Yeah, well, yeah, the dot, we defined the inner product of A and B to be the trace of AB transpose. But what that is A11, B11 plus A12, B12 plus plus ANN, BNN. It's just the multiplying likewise components. This, well, okay, fine. So the thing that's lost in this is, well, I should shut up. I feel like I'm forgetting something. I don't see my... Oh, I think my solution might have an error in it at the moment. No. Maybe I'm wrong. Oh. was W here? It's the span. What I said about there being zeros on the diagonal was wrong. There's a error in my current solution. Like my current solution is in W, which is not correct. The projection under W perp of A should be an element of W perp, okay? And my current solution is an element of W, which means that my current solution, what I did is I forgot to subtract this from A. My current solution just has projection W, but anyway. So there's a mistake in my current. I need to fix that. Anyway, there's, this, what's this have on the, there's going to be A and D on the diagonal, right? And then, we get B minus 1/2 of that. So there's other things on the off diagonals, but there's A and D on the diagonal, so.
And like we were talking about yesterday afternoon, for D, to find the closest point, we just plug the matrix into the projection of W.
Right. Oh, sorry, I'm so annoyed by my current answer. I got my current answer's got the anyway. Shut up. Hopefully, I'll fix that before I post it. Yeah.
Can we talk about the kernel? I know this isn't related.
No, we can always talk about older things. You want to talk about kernel? What do you want to talk about?
I think I know what it is, but at the same time, I think I tell myself that I don't know. So then it stresses me out.
So the kernel is stressing you out. What is the kernel?
Kernel is when something equals 0.
When something equals 0, that is definitely part of it. So first of all, what's the kernel about? We're talking about a linear transformation from V to W. All right. Most of the time lately in the course, we've been talking about linear transformations from a vector space to itself, right? But before that, we talked about linear transformations from any old vector space to any other old vector space, right? And in that context, we define kernel. And the kernel of T is something, well, one way we say is it's the inverse image of 0. So the inverse image of 0, that's kind of a fancy way of defining. So basically, this is probably not helping you. I'm defining one thing with something you're less certain about, right? So that's not maybe not helpful, but what it is first of all, it's a subset of the domain x in V, all right, such that T of x is equal to 0. This is the kernel. The main thing to know about the kernel is that if it's 0, and we have a linear transformation, that means the linear transformation is 1-to-1. If you happen to have a linear transformation from a vector space to itself, there's a connection between 1-to-1 and onto, right? Like if it happens to be an endomorphism, a transformation from the vector space to itself, if it's 1-to-1, it's also automatically onto. So like kernel being 0 for an endomorphism actually gives us, in the finite dimensional case, that it's an isomorphism. Because 1-to-1, if and only if onto, if and only if a bijective linear transformation for a linear transformation on a finite dimensional vector space. But, okay, that's just a crash review. Now, how do you actually calculate this for problems, right? So, let's see here. If we had something like T of xy equal to x plus y, y plus x, y, maybe that's too uninteresting. Let's do 2x plus 2y. There we go. So here, excuse me, for for xy in R2. Now we'd be looking at a linear transformation from what? From R2 to R3, right? So in this case, we could write t of xy equal to 1, 1, 1, 1, 2, 2, xy like that, right? So that's the standard matrix. And like the thing here is t acting on v is equal to the standard matrix of t, right, times the vector. So if you put that if that's equal to 0, I mean, this is sort of the critical calculation that shows you that to calculate the kernel of a linear transformation on column vectors, there's this pretty nice relation here, which is that v is in the kernel of t if and only if v is in the null space of the standard matrix of t. But we know how to, I mean, I don't know, however you want to approach this, you can just calculate it, but so if we look at, standard matrix of t, what do we got? We got 1, 1, 1, 1, 2, 2, right? So you do subtract row 2, subtract row 1 from row 2, subtract 2 row times row 1 from row 3. That's as simple as it gets. From that, we can read that, if we look at v equal to x1, x2, it equals what? I mean, we're going to have x1 plus x2 equal to 0, right? That's the equation that defines the null space. And so to find the null space basis, we've got, minus x2. x2, I'm using the free parameter to be safe, but here it really doesn't matter. You could use x1 or x2. But keeping with my more general, trying to get into good habits. So there you go. The kernel of t is the span minus 1, 1 in this case.
That's actually not perfect.
No. So for a transformation on column vectors, we just calculate the null space. Basis for the null space will give us a basis for the kernel. The nullity, which we usually use nu of t, or nullity, is the dimension of the kernel. In this case, it's 1.
Because 1, 0, 0, 1, 0, 0 are the same.
Because this is a basis for the null space, it's got one thing. So the dimension of the null space is the dimension of the kernel, or which is equal to the dimension of the null space.
So if, let's say, for example, the bottom 0, 0 was, for some reason, 7 and 2. That would give us 2 equations, and then so our nullity would be 2.
Our nullity would be 0 in that case, because we'd have 2 independent equations, and when we work that out, we'd only have the 0 solution. Okay. If these were different, then the rank of the matrix would be 2, because you'd have 2 linearly independent columns. And the more general thing here is that the nullity of t plus the rank of t is equal to the dimension of v. That's for that's for just t in the wild, from abstract vector space v to abstract vector space w of a finite dimension. But if we're talking about column vectors, then I can be more specific. There's a relation between, for a transformation on Rn to Rm or Cn to Cm. If you're working column vectors, the nullity is the number of non-pivots in standard matrix of T. Excuse me. And the rank is the number of pivot columns. In the standard matrix of T. The number of pivot columns in the standard matrix of T is also the dimension of the column space. It's the maximal number of linearly independent columns for the standard matrix and so forth. So these ideas are all kind of intertwangled and working together. Yeah.
So I'm like making sure my sentence.
Uh-huh.
The columns is when there's 1, 1, 1, 1, 1, or where the ones would be in the right spot.
Yeah, the pivot columns in the RREF will be the standard basis once we're done. But it is possible to figure out which are the pivots without actually getting to that point, right? Like if I gave you, if you had a standard matrix for some transformation, and it was like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. I can look at that and I can tell you immediately that the rank of that matrix is 4. How do I know that? Well, let me tell you how I know that. I'm supposing these are zeros. So one of the theorems we have is that if a matrix is upper triangular, then the eigenvalues are on the diagonal. So this matrix has eigenvalues 1, 5, 8, and 10. Those are distinct. Distinct eigenvalues give you distinct eigenvectors in the sense that the eigenspaces for eigenvalue 1, 5, 8, and 10 are distinct. They're independent, which means that I have an eigenbasis. In fact, this matrix is diagonalizable. It can be diagonalized to 1, 5, 8, 10 on the diagonal. You can get rid of the stuff above. So the nullity of this matrix would be 0 because it has rank 4. The kernel of this matrix would be 0. The linear transformation from R4 to R4, which this matrix corresponds to, would be an isomorphism. It would be 1 to 1 and on to from R4 to R4. So, but I can tell you, getting back to my point, was this, and this, these are pivot columns. Like, I can tell you that this is going to row reduce to 1, 1, 1, 1 with zeros elsewhere. I can tell you that without doing a single row operation. Like, I don't actually have to get to the reduced row echelon form to see that, because I have kind of other insights into the matrix. So I'm just trying to tell you that because I said it's the number of pivot columns, but that doesn't mean you actually have to get to the end of the row reduction to see what is a quote-unquote pivot column. There's other ideas at play here. Let's look at a kernel example which is not a column, since you have, concerns. So if we had, let's see here, how about T of f of x is equal to x times f prime prime of x for T mapping P4R to P4R. So possibly quartic polynomials, the possibly quartic polynomials, our mapping is x times the second derivative. So if f of x is in the kernel, that means that x times f prime prime of x equal to 0. But what does that mean? That means that since this is true for all x, f prime prime of x is equal to 0, right? And so for this one, rather than doing row reduction or anything, I use calculus. I would integrate twice. That would be the easiest way for me to see it. So integrating once gives me f prime of x equals to c1. Integrate again, I get f of x equal to c1x plus c2.
And those are just the constants that you have to add and integrate when you don't have counts.
Right, yeah. And so this says to me that the kernel of T is the span of 1 and x. That's what I can see from that. because f of x is c1x plus c2, and that's an arbitrary thing in the kernel. That's what it looks like. So that means the kernel is formed by a span of 1 and x, which are linearly independent. We proved that elsewhere. It's part of the monomial basis. A subset of a linearly independent set is linearly independent. And so this shows us that the nullity here is 2.
Could you also write it as x comma 1, or does it?
Yeah, oh yeah, you could, x comma 1 be fine. Now, for this one here, by the way, we can make beta equal to something. I'll put the kernel basis last. And we can choose gamma equal to something such that the matrix of T with respect to beta gamma equals to 1, 0, 0, 1, and then zeros, which I'll write out fine. So if this is equal to the T of something, gamma coordinates, T of something, gamma coordinates, T of 1, T of x. The point is that T of 1 is 0, T of x is 0. So these are 0, which makes these two last columns 0. Because we just proved that 1 and x are in the kernel. That's right. And so, how do I complete 1x to a basis for P4? Uh-huh. Or you said you originally said x3 and x2, and that would also not be wrong. It doesn't. There's many choices here, but there's one. You could even do x squared plus x cubed, x squared minus x cubed. There's infinitely many choices, but this is a lazy one. I like it. So all you do is put t of x squared for here, and you put t of x cubed for there. That makes, that makes this the first thing in the gamma basis, which puts a 1 here. That makes that the second thing in the gamma basis, which puts a 0, 1, 0, 0 here. And then whatever I put over here, I'm not sure yet. What is t of x squared? Right, yeah, it's x times 2, it's 2x, right? And t of x cubed is x times, what's the second derivative of x cubed? 3x squared, 6x, right? So you're looking at 2x and 6x squared. That's actually what this is. This is 2x, this is 6x squared. What do I have to put here and here to complete to a basis? I need something that I haven't already used. I've used up my x, I've used up my x squared.
Oh, so then you just need a 1 and x.
Yep. That's how this game is played. So there's a problem on your last test like this, right? I like this problem because it has all of the ingredients that are important to the middle third of the course. It has constructing a basis, it has calculating a kernel, it has understanding what the range looks like, it has meaningful use of coordinates. I test on many, many things by this problem all at once. And students find it challenging but not impossible, so it's right where I want to be in a test in here. So yeah.
When you wrote the T of beta gamma, so 1, 0, 0, 1 came from the span. I think I get confused with how I'm supposed to write everything in the matrix.
Oh, in here?
Yeah.
Well, generically speaking, our definition for abstract matrix, remember, we do T of the first thing in the beta basis. So here beta, V1, V2, Vn, let's say gamma, W1, W2, Wm. So our definition was that the first column, we take the first thing in the domain basis, and we calculate the coordinate vector of it with respect to the range basis, or the codomain basis. Then the second column, we do t of the second thing in the domain basis, and calculate the coordinate vector of it with respect to the codomain basis, and so forth and so on. Eventually, we get to the last one, which would be t of v n. We calculate the coordinates with respect to the gamma basis. This means that any vector in the gamma basis will be an element of f m, right? And so these are, it's m tall, and there are n of these. So this is an m by n matrix. That's how. Now the reason, so like I put 1 and x at the end here because I know that makes these 0, which gives me the zeros over here. You know, I haven't stated the problem where, you know, this is a problem I usually state, like find a basis that makes the matrix for the transformation, the identity matrix, with zeros elsewhere. And so the game you play is to put the kernel basis last in the domain basis, and then put whatever you need to complete that, you know, things which are outside the kernel, namely x squared and x cubed, because they map to this and that, which are non-zero. We fill out the start of the basis like that. And then to make this be 1 and make this be, you know, to make this be E1, make this be E2, we just make what they map to, the things, the corresponding first things in the second basis. And then finally, at the end of that, we have to complete that to this. But listen, this is, you know, finding the kernel by integration, that was special to this problem. If I had done the same thing, but said, say, plus f prime of x, then that would have rained on our parade. If I do that, then we can't just integrate, right? We'd have to actually work it out a different way. Let's look at that. So this here, if we said f of x is ax cubed plus bx squared plus cx plus d, right? Again, if I set this equal to 0, I don't think I can just integrate it, all right? Yeah, it's early. And then, so what's f prime of x? 3ax squared plus 2bx plus c. F prime prime of x, 6ax plus 2b, right? So we take those, we put them up in here, we get x times 6ax plus b plus 3ax squared plus 2bx plus c. That's all equal to 0 for f of x, for ax cubed plus bx squared plus cx plus d in the kernel. And then what does that look like? I mean, what can we find the basis in this case? Well, see, you know, I just have to, it's a polynomial equation. This one we're actually going to, you know, what's it going to look like? Well, let's see here. I've got x squared times 6a plus 3a, x times b plus 2b, right, plus c equal to 0. So it looks like, well, this one's actually really simple. So we've got x squared times, 9ax squared plus 3bx plus c equal to 0. I think most of you guys will tell me, so a equals b equals c equals 0, right? Because like the coefficient of x squared, the coefficient of x and the constant term have to separately vanish, right? And so what's the kernel? Looks like just D, such that D, almost everything. We still have the constant term, right? So that is, the span of 1. So that this mapping has nullity 1 because the dimension of the kernel is 1. The range here would be 3-dimensional, for what it's worth. Yeah, there's... Oh, There is actually a shortcut way to do this with calculus. Some of you guys aren't going to like this. So I'm going to rewrite it like this. This is x times d dx of f prime of x, right? dx dx f prime of x. So by the product rule, that's d dx of x times f prime of x. So if I set that equal to 0, that means that x times f prime of x is equal to a constant. But the only way that x times f prime of x can be equal to a constant is if f prime of x is equal to 0. And the only way f prime of x can be equal to 0 is that f of x is just equal to a constant. So we're back where we started, yeah. I mean, so calculus or direct order by order polynomial algebra should get you to the same place. All right, well, I think we still have 10 minutes, right? Let me talk about, I said I would talk about the other problems, right? So problem 139. So what problem, all right, so part A is to show that G is a symmetric bilinear form on R4. So you'll have to look up what that means. What's a symmetric bilinear form? I haven't defined it in class yet, have I? No, I have not. You are right. But a symmetric bilinear form, what's a bilinear form? A bilinear form is something like this. It goes from V cross V. And if we're talking about the reals to the reals again, this becomes a bilinear form if like G of AX plus B, comma, AX plus BY, comma, Z is equal to A, G of XZ plus B, G of YZ. And likewise, G of X, comma, BY plus CZ equals G of B, G of XY plus C, G of XZ. So in other words, bilinear means it's linear in each entry. And symmetric means that G of XY is equal to G of YX. These should be true for all X, Y, and Z in the vector space in question. So this problem, you've got G of VW, or let's say G, I'll use X and Y just to make it look the same. XY is X transpose eta Y, where eta is a specific 4x4 matrix. So proving bilinearity is a breeze here because it's just formed by matrix multiplication with either a row or a column on either side. So you can use properties of matrix multiplication to do part A. It's not a big deal. Symmetric, well, symmetric is not bad either. So this is a number, right? Agree? What can we do with a number? Well, no, let's say one of the things we forget sometimes, but 3 is equal to 3 transpose. So, I don't know. Let me not be that way. I'm just telling you, you can investigate it, work out the formula. You'll be able to show that G of XY is equal to G of YX. It's not hard. Why is G not an inner product? To see that G is not an inner product for part B, my advice would be look at X equal to 1, 1, 0, 0. Investigate the fourth axiom of inner product. What did that say? It said that inner product of X and X is equal to what? Is equal to 0 if and only if, right? Well, this isn't the axiom, but this is something we proved. The inner product of X, well, we could have proved if I'd done it. The inner product of X and X is equal to 0 if and only if X is equal to 0. if you look at this vector 1, 1, 0, 0 for this possible inner product, you'll see that, in fact, the inner product of this with itself is 0. It's an example of what's called a null vector. A null vector is a vector which is non-zero and yet has 0 quote-unquote inner product. Of course, this is not an inner product. It's like I said, some people would say it's a pseudo inner product. Some people would say it's a metric. That terminology is from physics. Now, part C, I say if you restrict it to that subspace, you do get an inner product. I'll let you look at that. And in contrast, part D, I'm kind of giving you the same advice I'm giving right here, which is to look at E1 plus E2. That's 1, 1, 0, 0. So the reason, if you restrict G to that, I'm pretty sure that the metric is 0 on that curve, on that C, that line through the origin. But one of the theorems we had for an inner product was if you restrict to any subspace, you get an inner product. In contrast, for a metric, if we restrict to the wrong kind of subspace, we don't have a metric anymore. So that's the moral of the story here, is difference between inner product and metric. Problem 140. I have trace of t equals to the square root of 2, right? Yeah, problem 140.
Oh, yeah. I didn't look at B.
Oh, that's okay. Yeah, trace of t. Let's see what kind of advice. Let me just a second here. I'll tell you my advice.
This is kind of what we were doing in class.
Yeah, there's some fussy details here, I think. So I would say, so the wrong way to do it is to look at A transpose A equals to I. Like, do not do this. Instead, as you're trying to understand what does it mean for A to be an SO2, so I mean, for A to be an SO2, you have this and the determinant of A equals to 1, right? All right. So in the past, when I have students that have tried to do this, you take A, B, C, D for your A and work out the conditions here, then they're nonlinear. It's horrible. It's really hard to see through. But if you trade this for A transpose equals to A inverse, this is much nicer to look at because that gives you linear equations for the most on the entries, because the determinant is 1. So the formula for 2 by 2 inverse is nicer than you might think. So I would say my advice would be make sure you look at this for A, B, C, D and find reasons that you can identify A, B, C, and D as cosines and sines. What does it take to find a reason to identify a number as a cosine or sine? You need that number is between -1 and 1, right? And for one of them to be sine and one of them to be cosine, you need that the sum of the squares of the numbers is 1. If you have those two things, you can argue that those numbers can be identified as the sine and cosine of an angle. So that's what you're trying to do there. It's not. This is less linear algebra, more sort of just algebra. And now, one of the things I should have told you guys last time is an isometry is, well, excuse me. Oh, yeah. We looked at isometries last class. I didn't call them that. A orthogonal transformation is an isometry of the dot product. A unitary transformation is an isometry of the complex inner product. So isometry just means same measure. It preserves the length of vectors. But there's also a theorem, a linear isometry. And isometries are more, the thing is, orthogonal transformation implies isometry. However, isometry does not imply orthogonal transformation, generally speaking. There's other kinds of isometries, like you can shift by a vector translation. That's also an isometry. But anyway, I think we're out of time. I'll talk more about these next time we have a chance. But let me just say that the solutions to problem 141 and 142 are not that easy. There's some kind of subtle thinking involved in there that I'll tell you more in person if you ask me about. So anyway, sorry I didn't spend more time, but you had good questions today, so be it.